Random variable. We will learn about random variable and the use of random variable and the properties of random variable and the different types of random variable. So what is a random variable? A random variable is a variable that may obtain any value within our sample space at a given probability. For example, if you toss a coin and your random variable is the number of heads that will appear in tossing of the coin. There are two possibilities. Either you will have 0 heads or you will have 1 head, each with the probability 0.5 and 0.5. So in this experiment, a random variable is the one which keeps track of the number of heads in a coin toss. If you are tossing two coins, there are three possibilities. Either you have 0 head, 1 head or 2 head with their associated probability. Random variables can be discrete or they can be continuous. Outcome of a dice roll is a discrete random variable because there are only 6 outcomes possible. 1, 2, 3, 4, 5, 6. And each have a probability of 1 by 6. On the other hand, we have continuous random variable. Maybe let's say consider time taken to complete a task. It can assume infinite values, and as a result, we may not be able to compute the probabilities of each of these possibilities. So in such a case, what we do is we, instead of finding the probability of a particular occurrence, we look for a range of values and we try to determine the probability of occurrence of values between those endpoints. Random variables with their associated chances of occurrence is called as a probability distribution. So probability distribution gives us the complete nature of a random variable. We started with the data in the beginning and came up with the description which summarized the data as mean and standard deviation. Now the summarization is a lossy transformation. While lossy transformation I mean is from data you can come to the summaries, but with summaries you cannot go back to the data. In case we have the probability distribution plus the data summary, we can reproduce or synthesize the data again having the same characteristics even if the values are not exactly same as the data, but we have a data set which follows a certain characteristics, certain nature, certain distribution. So this becomes a very important feature in our inferential statistics. Probability distribution can be displayed as a table or a graph. Let me show you an example of a table. Let us say count of heads in 3 coin tosses. There is a probability of 0 head with 1 by 8 probability, 1 head with 3 by 8, 2 head with 3 by 8 and 3 heads with 1 by 8 probability. This is a tabular representation of the probability distribution. Let's say commuting time to reach a school. People may take from 0 to 15 minutes, 15 to 30 minutes, and so on until 90 minutes. And we may have the probability distribution, which is 10% take 0 to 15 minutes and 20% for the next 4 categories, which is 15 to 30, 30 to 45, 45 to 60, and 60 to 75, and finally 75 to 90. Now this tabular data can also be represented graphically. So here we use the bar chart to represent the discrete random variables distribution. For continuous random variable, we use a area chart. The sum total of the probabilities in a distribution is always 1. The sum total of the area under this curve in a continuous variable probability distribution is also equal to 1. Now, when we develop a distribution from a data set, we get an empirical distribution. The empirical distribution takes a lot of memory space, a lot of computational effort. So what we do is we try to approximate an empirical distribution with a naturally occurring distributions. We'll talk about some of those distributions. Like in discrete random variable, we will have binomial distribution and Poisson distribution are examples. Whereas uniform distribution and normal distribution are examples of continuous random variable. We can compute the expected value and variance using the formula xpx summation over all the values for mu and x minus mu whole square times p of x summation over all the values of x to get the variance square. Same thing in case of continuous random variable, we use the integral. So let's talk about binomial distribution. Binomial distribution is a naturally occurring distribution which models the likelihood of R successes in n independent trials when each trial has a probability P of success. We can see the formula for this is NCR, means number of combinations in a sample space of n when R successes are achieved, multiplied by P to the power R times 1 minus P to the power n minus R. The binomial distribution mu has a mean of NP and a standard deviation of root of NPQ, where Q is 1 minus P. Similarly, we have another standard distribution called Poisson distribution, which models the number of times a specific event occurs within a fixed time interval of time or space. It is given by e to the power minus lambda times lambda to the power x divided by x factorial. Now, lambda is a parameter of Poisson distribution where the mean and the standard deviation are both equal to it. A classic example of a Poisson distribution could be number of people arriving in a specific time period in a airport. It can also be used to model the number of people visiting a hospital or a university or people arriving at some public property. Now let's talk about the continuous distribution. Uniform distribution is one of the simplest continuous variable distribution which models the experiment where each outcome in a range has an equal chance of occurring. And the probability, which is given by the area bound between x1 and x2, is where b minus a is the total width of the values, the minimum and the maximum of the x, and x2 minus x1 divided by that total length gives us the probability of occurrence of a random event which will be between x1 and x2. The mean value is given by a plus b by 2 and the sigma is given by b minus a whole square divided by 12. Let's talk about another continuous variable distribution, which is normal distribution. Normal distribution is a theoretical distribution. It is symmetric with same mean, median and mode, and the function is given by 1 by root of 2 pi times e to the power minus x square by 2. It is also called as Gaussian distribution as it was invented by Gauss. The importance of normal distribution is that many of the naturally occurring phenomena in the social sciences and in nature follow a normal distribution. Example, distribution of heights of the people about 20 years of age, the weight of the people in a particular age group, the number of apples on similarly aged apple trees. These all follow a normal distribution wherein a large number of values are centered at the mean with the dispersion on the either side, such that 68% of the values are within one standard deviation of the mean, 95% values are within two standard deviations of the mean, and 99.3% values are within three standard deviations of the mean. Normal distribution is commonly used in modeling many of the social science experiments, which makes our mathematics elegant. Once we have the data, we can do the lossy transformation by finding the data summarization. When data summarization Those are called as the parameters of the population. In conjunction with the nature of the data or the probability distribution of the random variable, we can go back to synthesizing the data, which will have the same properties as the summary measure and the nature determined by the probability distribution. This makes a very powerful tool in our hand to synthesize and experiment several phenomena in a laboratory. The mathematics involved with the normal distribution is a lot more elegant compared to the mathematics involved with the discrete distribution. So we often transform the discrete distribution into normal distribution, and since it is an approximation, we use what we call as continuity correction. So here I am showing you an example of a conversion of a binomial distribution to normal distribution. These bar charts indicate a discrete binomial distribution, and this orange line which is superimposed on top of this bar chart is a normal distribution. It is reasonable approximation to model the discrete binomial distribution as normal distribution. The formulas are given here, where we consider, let's say, if you want to find the probability of x equal to a, let's say a be this number. In that case, we can take 0.5 plus and minus and find the area within this boundaries of the plus and minus a to define the approximate probability using the normal function. Typically for the large data sets, the probabilities are reasonably a good approximation to several decimal place significances.